problem is about heating a cup of coffee. So I'm going to draw a sketch of what's going on. This is an electric heater plugged into a wall outlet. So I'm going to say this is my little heater. I'm imagining it more like a hot plate. Here's my little hot plate. And we're warming up a cup of coffee. And this hot plate is plugged into the wall. I need to have two wires, one going into the hot plate and one out. And let's see, here's my wall outlet. Okay. All right, the wall outlet has two prongs because one wire goes in one prong, the other goes in the other prong. We usually don't see that. But yeah, the two prongs in your wall outlet, one is at high potential, one is at low potential. This is the equivalent of your battery because it provides a constant potential difference. There's my sketch, and let's see what else I know here. I know the current in the wire is 2.5 amps, and the potential difference from that outlet is 120 volts, and this coffee is going to get heated for 2 minutes. Okay, that's my sketch. Now it says to draw a circuit diagram of this and then an energy bar chart. So instead of the wall outlet, I have a battery. Okay, here's my high potential and my low potential. The potential of this wall outlet or battery is 120 volts. And that heater I can treat as a single resistor. Here's my resistor. Right, the resistor is any device that we are operating. Okay, and the current, conventional current, goes from high to low potential. That's the flow of positive charges, even though we know that's not how it works. There's my conventional current. Okay, and now an energy bar chart for a system consisting of the coffee. All right, well, initially this coffee does not have kinetic energy or gravitational energy or elastic energy. We could just say that it has no energy. And then heating is done by this heater, right? That's Q, heating. And that heating will equal the change in internal energy or thermal energy of this coffee. So I'm going to say that heater did 2 boxes of heating, and now the internal energy of the coffee increased. Remember that internal energy is proportional to temperature, right? This is such a fun problem because it brings in thermodynamics, which we've already done. So that's what's going on here. Energy is being transferred to the coffee via heating, and the internal energy of the coffee increases. Okay, now it says to calculate the resistance of the heater. All right, the resistance of the heater. I'm going to use Ohm's law. Resistance is the ratio of the potential difference across the device divided by the current going through the device. That's Ohm's law. And let me explain why I chose that. Resistance is the ratio of the potential difference across the device and current through the device. Okay, so that's why I chose to use Ohm's law. and I know my potential difference in current. So I can just put in the values here. The potential difference across the device is 120 volts. I know that because this wire, okay, I'm coloring it green, is connected to the high potential of the battery. This is high potential. And then the other wire, I think I'll color it black. This is connected to low potential. So there's a change in potential across this resistor of 120 volts. All right. The current is 2.5 amps. And if I put that into a calculator, I'm going to get 48 ohms. Okay, an ohm is a new unit for us. So that's my resistance, and now I need to find the amount of heating done to the system by the heater. Okay, which formula can I use for that? I think I'm going to use this formula for power because I know current and potential difference. I know current and potential difference, so I can find and then I'll use this power to help me figure out the heating. Okay, current 2.5 amps. Potential difference is 120 volts. And if I put that into a calculator, I'll get 300 watts. Okay, that's not the end of my question. Okay, so there's my power. Okay, but I have to figure out heating. So I also know that power is equal to work over time. It's a measure of how fast work is done. But work is also equal to the change in energy. Well, the change in energy in this problem is the heating. There was no working done on the coffee, there was heating done. So the power of this heater would equal the heating done in a certain amount of time. A more powerful heater will do more heating in less time than a less powerful one. So I pick this equation. I explain every general equation that I use, I explain why I chose it. Power is a measure of how fast working or heating is done. Okay, so I need to find the heating here. I'm going to rearrange this equation for heating. My heating will be power times time. And okay, great, I know these things. The power is 300 watts. And then my time, I need this in seconds. Let's just do a quick unit conversion. 2 minutes. Okay, minute, second. 1 minute is 60 seconds. So 2 minutes is 120 seconds. So when I do that out, I get 36,000 joules. All right, so I explained each general equation. The last piece of this is to evaluate the solution. How do I know if my answer is reasonable or not? For evaluation, I usually look at the sign, the unit, and then the value. Okay, so I usually do sign, unit, and value. I'll do it up here. Okay. For the sign, I'm not expecting any negative numbers because we're adding energy into the system, but also resistance can't be negative. Power is not negative either, so sign doesn't really tell me much here. I'm not even going to write that down. The units, did I do any unit analysis? Let's check this out. I can do some unit analysis here. Yeah, I'm going to make a note here. The sign is not really relevant. It should be positive. Okay, resistance, power. Are positive. Okay, the unit. All right, let me check my power unit. I have a watt times a second. A watt is a joule per second. So I've got a joule per second times a second, which equals a joule. So my unit analysis works there. For my resistance, I have this volt over an amp. Let's see if we can get anywhere with that. An amp, I don't know if we can. That's charge, so that would be coulomb over a second. A volt, what's a volt? That's our unit for V field. A volt is a joule over a coulomb. And so if I were to do that out, a volt over an amp, that's a joule over a coulomb over a second. All right, well that's a joule over a coulomb times a second, because I would flip this, right? Over a coulomb. You know, I'm really not getting anywhere with this. That's a joule times a second over a coulomb squared. Is that what an ohm is? I don't know. Ohm is a basic unit, so I don't think I can actually get anywhere with that. Okay, so the unit analysis is really not helpful. But my power unit worked out. I'll just put the power stuff here. Okay, the last one is the reasonability or the value. Let's do that. We're talking about how reasonable is the value. I had fun thinking about how reasonable that number is. Well, I thought about, geez, if you have a cup of coffee, I mean, how much coffee is that? I said that was about 1/4 of a kilogram of coffee, right? Maybe a cup of coffee is like a cup of water, and that might be 1/2 pound. And then I said, well, if you had a cup of coffee at room temperature and you wanted to heat it, well, what temperature do you want your coffee to go to? And I actually looked up that the ideal temperature of coffee when you serve it is 185 degrees Celsius. I'm sorry, degrees Fahrenheit, which is 85 degrees Celsius. And then I thought about the specific heat of water. And so I just decided what would be kind of a reasonable amount of heating you would need to heat up a cup of coffee. And here's how I thought about that. This is my other formula for heating. Heating is the mass times C, which is the specific heat, times the change in temperature. And I just threw in some estimated values. I said that the cup of coffee is about half a pound, and that would be 0.25 kilograms. Specific heat of water, that's 4,182 joules per degree Celsius times kilogram. And then the change in temperature, I just kind of estimated. I said, well, what if this coffee started at room temperature and then it went up to 185 degrees? So let's just say that our change in temperature was the initial temperature 20 degrees Celsius, that's room temperature. Oops, let me start with my final temperature. Let's say that we want to serve the coffee at 185 degrees Fahrenheit. So 85 degrees Celsius is the ideal temperature of coffee. And let's say the coffee started at room temperature. That would be the change in temperature of this cup of coffee. I decided to put all that into a calculator, and it came up to 68,000 joules. So this is the amount of heat needed to raise the temperature of a cup of coffee at room temperature to 85 degrees Celsius, which is the ideal temperature to serve coffee. I found this on like a Starbucks website. And now I know for when I'm entertaining in a post-COVID world. So all that said, I think that the fact that I got 36,000 joules to raise the temperature of this cup of coffee seems reasonable. If I just leave that heater in, or leave the coffee on the heater for another 2 minutes, then I could probably serve the coffee and have a very lovely coffee with a friend that is social distance and outside. Okay, so it does feel reasonable. Let me make sure I've written this. So my answer of 36,000 joules seems reasonable. All right, I had fun with that one. I didn't know some of these things about coffee.